So now let's go into some simple Python code, right? Very simple code, very easy to understand. But there is an important point I want to drive. Okay, so let's go here. Again, the code for this is very, very simple. You don't have to implement it. While you can, it's fairly simple. So SciPy stats has this function. Okay, so again, let's use the same setup that we discussed in the previous session also. So imagine if I have 100 samples in the control, 100 samples in the treatment. Okay, and I'm generating. Okay, so let's take a small detour. Okay, let's explain Mann-Whitney U code, then I'll do the simple simulation experiments. Okay, so look at this. I have only 100 samples, and I'm generating XC and XT from Pareto distributions very close, 10 and 9. Look at this, 10 and 9, very close. Small samples, very close distributions. This is where your permutation testing failed. But I'm like, let's see. So what this does now is, I just have these two random variables. I just pass it to a function like this. I just pass it to this function. I don't have to implement everything from scratch. Understanding is important. Ability to implement is important. But in our case, in the interest of time, we'll just see this. What this does is it takes each XCI and each XTJ and it will compare them, compute the U statistic, and return us the p-value, right? It will do all of that. It's going to return us what is the U value, what is the test statistic, and what is the p-value. Let's just print the p-value here. Okay. So again, the fun part here is this. Okay, so let's write this down. Again, this is very important. So Mann-Whitney U versus permutation testing. Okay, so what all values do we have here? We have N, M, XC alpha, XT alpha, okay, and the p-value. Okay, I'm just making a quick note of all this. Okay, so we have 100, this is 10.0, this is 9.0, right? And when we computed the whole Mann-Whitney U, we got 3.8%. Okay, the p-value that we got is 3.8%. Am I right? Yes, this is 3.8%. Now, on the other hand, the same thing, the permutation testing. If I take 100, this is 10, this is 9. So the key thing here is small samples, small sample size, not too large, and the distributions are close. In such a case, even though the distributions are close, the Mann-Whitney U, even with just 100 points, clearly said that we will reject the null hypothesis. This basically means reject null hypothesis, right? It's behaving as we expect, right? It's saying reject null hypothesis because they're different. And actually they're different. Now, what happens in the permutation testing? Let's go and run the same code that we ran a while ago. What happens here? 100, let's assume this is 10,000. Let's give maximum number of resamplings. Here also the Pareto distribution is 10 and 9. Exact same setup, right? Number of resamplings, keep increasing it, no problem. Give as many resamplings as you want. Okay, so what is the p-value here? The p-value here is 8.73%. Okay, so the p-value that we had here is 8.73%, which means in this case we would have accepted the null hypothesis. Look at this. In this case, we would have accepted the null hypothesis that XC is same as XT. We're making an error, right? If you think about it, we made an error here. We made an error. Ask yourself what type of error it is. Look at this. Actually, in this case, because these two distributions are different, alternative hypothesis is true. The alternative hypothesis is true, but in permutation testing, we are saying that the null hypothesis is true, right? So let's go back here. Let's go back to our slide, okay? Again, some of you are confused when I asked you in the chat window, so let's go back to the slide. Okay. So what do we have? We have a case where alternative hypothesis is actually true, but we accepted the null hypothesis, which means it is type 2 error. So this is basically type 2 error. While this was perfect. Look at this, same number of samples, same distributions, your Mann-Whitney U is more powerful than your permutation test because it is behaving as we expect while the permutation test was doing a type 2 error. Right? Very important, very simple experiment, right? And you might wonder, hey, why is Mann-Whitney U so powerful as compared to permutation testing? Right? I mean, that's a valid question to ask. And there are a couple of reasons for it. Okay. And that's why it's also very popularly used in the industry. Now, a couple of reasons. So let's go through those. Okay. So a couple of reasons. The first important reason here is Mann-Whitney U is comparing all pairs. Let's not forget that. And we know that the test statistic has a nice underlying distribution. Right? The permutation testing is only comparing the medians and not all pairs. Remember, it's only at least the permutation test that we designed is comparing medians. And the test statistic, which is difference of medians, has no underlying distribution that we can leverage, thereby making Mann-Whitney U a better non-parametric test than permutation test. But there is still a catch. Permutation test is still powerful when you want to compute something like some measures around your random variables. Suppose if you have a random variable xc and xt, what you want to compute are not the distributions, but some function of them, like a median. Suppose you want to compare the median of this and the median of this. You don't want to compare the whole distribution. Or you want to compute the 99th percentile value and the 99th percentile value. In such a case, permutation test is still very, very powerful. Mann-Whitney test is comparing two distributions altogether using all pairs, again, using the power that U is normally distributed. Now, somebody asked this question, what if N and M are not large? If I recall well, still U has a very nice distribution. Let me just quickly check it. Mann-Whitney U, Wikipedia. U statistic, okay, calculations. Okay, so simple logic here, right? So when sample sizes are approximately 20, the normal distribution is a fairly good approximation, or else there are books, and most software has this, which has tabulated the distribution of U. Again, that's a boundary case, right? You can actually look at a table and say, hey, if N and M are small, let's assume both of them are equals to 10 and 12. Let's just say if they are this, then what is the distribution of U? You can get that from, people have tabulated those tables. Right? These are like your logarithmic tables that some of you may have seen when you were younger. Okay. So the idea here is Mann-Whitney U is more powerful because of the way it works internally. That's the key. Okay, cool. Now, a quick recap of hypothesis testing is as follows. Always, whenever you're looking at any hypothesis test, look at what is the null hypothesis and what is the alternative hypothesis. Look at the underlying assumptions, because if you mess up the assumptions, everything goes for a toss. What is the test statistic? Does the test statistic, like our U, have a distribution? Does it have an underlying distribution? Or can I compute what is the area under the curve, like the one that we have done in permutation testing? Then you reject or accept based on the significance level. This is the standard drill that you do, right?